Looking for latency. In this video, we'll take a look at using some very helpful features inside of Wireshark to help pinpoint what exactly is causing the delay in our network. Is it the PC? Is it the path? Or is it the server? Let's begin. Back in the 90s, I worked for a movie-making company, a pretty big one. Their first initial was P, as in Paramount. And while I was there, I had the opportunity to help support the network and also the SQL servers that they were using as databases at that time. And the application development group, they wrote a program that when that user clicked on a button, it would take 60 seconds before the results would show up on their screen in some kind of a table or form that they had created. 60 seconds! Now the programming manager at the time said, you know what, here's the deal. It's taking 20 seconds for the computer to do its work, 20 seconds for the network to deliver the traffic, and 20 seconds for the SQL server on the back end to go ahead and look it up. Literally, this is the story that that person told. And so because I was with the group that was responsible for this portion, the network and the SQL Server backend, we had to go and find out really what was happening. I mean, we had a clue that there's no possible way it really took 40 seconds for all this work to happen. We talked to a couple of the programmers and we said, can you give us the exact calls, the SQL queries that your application is making? That's all we want. We put them in a batch file and we got like 20 computers. Back in those days, they had floppy drives available, so we'd boot off of a floppy, run a batch that would write a timestamp, issue all the queries against the SQL server, get all the responses, write another timestamp, and we had that running off of like 20 different machines. You know what we found out? That the entire trip from the PC to the server to do all the lookups and to get the responses, that all took about 6 to 7 seconds. So armed with this data, this intelligence, this knowledge, we came back and said, okay, here's the deal. All those calls that you're making for the network to get those, deliver those back to the PC, it's only 6 to 7 seconds. That means there's approximately 53 seconds that your application is taking to go ahead and do whatever it does in the background and combine all that data to make it nice and pretty for the user. So with that new information, they went back and they rewrote the application, or at least the portion that handled that graphical report. And I think they got it under 20 seconds, which is still an incredibly long period of time to wait for anything, even back in the 90s. So you might ask, okay, Keith, how exactly does this story relate to Wireshark? Well, with Wireshark, we could have measured, for example, how long it's taking for responses to come back. If we put Wireshark on the network, for example, let's say the PC was right here, and this is the server running SQL Server, we could have taken a look. We could have sniffed at point A, point B, point C, point D, anywhere, and taken a look at the request and the response to see that all that took under 6 or 7 seconds. That would have been another terrific option to help verify where the delays are. We could say, you know what, it's taking 7 seconds when these requests go out and the responses come back. So the delay must be at your PC, at your application, sitting on the computer. So latency is all about delay. And latency isn't just inconvenient. It also can wreck applications. For example, if we have a voice over IP application, if there's too much latency or jitter or the network conditions aren't good enough to support that, the voice over IP call is not going to be successful, and as a result, that application, voice over IP, will fail on that type of a network. When we boil it all down, if we have latency issues, they're really going to be one of 3 places. Either at the client, like for example at the PC or processes running on that computer, on the server, and that server, for example, if this is the server that we're trying to reach, either a web server or SQL server or what have you, it might have additional resources it calls on. So we ask Google for some information. Perhaps Google goes to a back end and asks another server for additional details, and that gets fed back. So it's very possible we have more than just a single device that we're making requests to, and that could also potentially cause a delay if this server is waiting on this server. The other delay could be the network. For example, let's say you have 1,000 users here, and this connection right here is running at 128 kilobits per second. Maybe it's a serial link, or for some crazy reason you've rate limited your Ethernet way down to a small speed. That indeed would cause a bottleneck because there's simply not enough bandwidth to support the traffic for thousands of users going through that teeny pipe, that small amount of bandwidth. That could be choking the entire network. We could also have devices that are simply overloaded. Maybe they're doing network address translation or intrusion prevention or some other service, and they are simply the bottleneck. So it could be any device or any link in the path between the source and destination for the path there and the return that could be causing a bottleneck, if there is one. So as I mentioned, we might have applications that are causing us grief, like in the case of my experience back in the 90s with the homegrown application. When I talk about back-end magic, I'm just referring to the fact that we could have a server that makes calls to another server who makes calls to another server, and any delay in any of those queries and responses could cause delays as well, and upper limits. That refers to something being maxed out. And that could refer to bandwidth that's maxed out, CPU utilization that's maxed out, the input-output on a server or function that's in the path. Anything that's not able to support the throughput that's being requested because of some really high level of utilization, that's causing a delay. So when we look at networks, it's really amazing that when this PC, for example, goes out to a web server on the internet, it's really the weakest link that's going to cause us the slowness. Whether it's this one right here or this server, or the PC itself that just can't process the content that comes back very fast and can't put it up on the screen. Any one of these items, if it's the weak link, could cause the whole process to slow down. Now, not all traffic between this user here going out to, for example, a few websites, not every single delay is going to impact that user. For example, let's say the customer goes out to a web page and the page, boom, hits and fills. And in the background, maybe on the toolbar or some other area, in the background, it's putting more icons up on the screen. So it's not really noticeable or a big deal to the user because they got the main page. And if the details around the edges fill in a few moments later, not a huge deal. So a little latency for non-critical items that we're asking for, again, are not a big impact on the user. Also, what I call goodbye messages. Let's say that this PC goes out to a web server, makes a request, there's a three-way handshake, we have the content that comes back, and after a very short period of time, the content's all delivered, maybe we have a goodbye message. So if there's a goodbye message that comes maybe 15 or 20 seconds after that session has been established, when there's no other activity, maybe it's just normal traffic, a normal three-way session coming to a close, that's not really going to impact the user if that's delayed or if that's later in the process. I mean, what does the user do? They close their browser, they go to lunch, they don't care. They're not even going to notice. There also could be lots of other traffic that's not critical to what the user cares about. For example, the user goes to a website, they see that website, but in the background, we're doing like 5 additional DNS requests, we're getting 5 or 6 different objects that are being pulled in, all queued up for that user, when the user doesn't even know that's happening. Unless, of course, they have a protocol analyzer running, then they can say, holy schnikers, look at all this stuff that's still pouring in. But from a visual perspective, they may not even notice. I still remember my first exposure to protocol analyzers back in the 80s. And back in the 80s, it was most of it was Token Ring that I was currently working with. And the protocol analyzers were dedicated computers like in a suitcase, like a sewing machine case that size that we have to carry around and plug in. But the concept is the same, to find out what's really happening. And one of the things I noticed right off the bat when we did our first traces was like, we looked at the data and we thought, oh, what's that? Is that okay? Is that normal? And that's a really good question. We absolutely deserve in our networks to find out what normal looks like. I mean, maybe there are a boatload of retransmissions during the normal course of events on your network. So if those are happening as a normal occurrence, we could do a couple things. One, say, okay, that's a normal level of retransmissions that are happening because of weighted random early detection or some other queuing mechanism that's causing that to happen to benefit other protocols. Or we could dive in and say, okay, this is not good. Well, how can we improve this? And depending on your environment, you may have both of those conversations as you take a look at what normal looks like. And maybe you'll find out that your normal has some issues that you definitely want to improve on. So you can take a look at what's causing that and then take steps to correct the problem if possible. But it's a really great idea because here's what happens if you don't have a baseline of your network traffic. There's a problem, you put the protocol analyzer in, or you capture the data using monitored ports or using a wiretap or whatever method you choose to use. You collect the data and then you start looking at it and you think, oh my gosh, I've got like 12,000 packets. Which ones of these are problems? Are they normal? Are they okay? And if you don't have a really good idea about the baseline of normal traffic on your network, without a baseline in place, in the heat of battle, if we did a protocol analysis, we might not know what normal, quote unquote, looks like, and that could be additionally challenging to help us in identifying a new problem above and beyond our baseline. So I'd strongly encourage you to take some samples of network traffic, start analyzing it, and find out what your normal traffic looks like. I alluded to this a moment ago, but there also might be quality of service that could be in place in your network where if congestion starts to occur, for example, there's just too much traffic for the network to support, the network devices, the switches and routers configured to support QoS might specifically be prioritizing some traffic and intentionally letting other traffic die based on how it was configured. For example, a voice call absolutely needs to make it on time to the destination for that voice application to work. Email, on the other hand, we can kill a few packets. It'll go ahead and retransmit, it'll recover that. It's not life-threatening. The application of email is not going to fail if in the background a few segments of data have to be retransmitted. So in an environment that has QoS, it very likely will favor voice traffic and allow other traffic that can survive a few lost segments to go ahead and automatically recover on its own. So if that's happening, we definitely want to be aware of that in our networks as well. So let's imagine that we have a couple users on our networks internally, and let's, for example, use these two. We have PC 10, which is Windows 8, and down here we have Ubuntu on the PC 20, and they're both on different networks. And my question is, if we're looking for latency based on these clients going out to the internet, where would we go ahead and trace? Where would we capture the data? And the answer is we'd likely want to capture it either here and here, or we could catch it on the trunk link, that would work, or here, or we could catch it here. So we have lots of options. What I'd like to do for this demonstration, let's go ahead and capture right here on this link. It is a trunk link, so we'll have that additional 802.1q header, which is pretty cool to look at as well. But if both of these users go out to the same resources and there's delays involved, we can then take a look with the capture and identify using that TCP delta. Is it the response that's taking time, or is the response coming back very quickly and it's the actual operating system or browser that's causing the delay in the user seeing it? So let's set up this scenario right now. The other thing I think we ought to do is let's go ahead and inject some latency into the network. Right here on R2, what we're going to do is we're going to set up generic traffic shaping for any traffic going this direction out the gig 1/0 interface if it's destined for the 10 subnet, which happens to be VLAN 10. So that way, regardless if we have web servers that are performing extremely well, we can increase the latency just to this subnet for any traffic. So we'll do that as well. So let's set up the traffic shaping on R2. On R2's console is a Cisco iOS router. The first thing we're going to do is go into configuration mode, and we're going to create an access list. The access list is simply saying this: if any traffic, IP version 4 traffic, is destined to the 172.16.10 subnet, which is VLAN 10, it's going to be a match. That's all this access list is going to say. We're going to use access list 110. Now, to apply this, what we're going to do is we're going to go into interface gig 1/0. That's the left-hand interface of R2. And we're going to say, you know what, Mr. R2, on this interface, we want you to traffic shape. We want you to limit traffic down to 64 kilobits per second if traffic matches that access list. And the command to do that is traffic shape group 110, referring to access list 110, and then the 64,000 parameter. Now, to verify the details of what it gave us, whatever we didn't specify, we got the defaults from iOS 4. I also simply want to verify that there's no current counters in place from any current activity on that VLAN. And let's go ahead and simply do a verification of statistics. Let's show traffic shape statistics. And what this will do, it'll tell us if there's any current limits that are currently in place. So right now, we've got no packets involved, no packets being delayed, and there's no active shaping because there's no traffic. And that would include traffic exceeding the 64 kilobits per second. So now that our traffic shaping is configured, let's go ahead and go to a couple PCs. We'll go to this guy. This is our Windows 8 machine. And down here we have our Unix box. It's actually a Linux box. And let's go ahead and launch some traffic, open up some browsers out to the internet out here. And the reply traffic, when it comes back to this subnet, we'll have the traffic shaping happening right here. And when traffic goes back to VLAN 20, there shouldn't be any traffic shaping at all. I also want to mention that these commands that I've added to do the generic traffic shaping on R2, I've also included in the Nugget Lab download area. So if you want to add the traffic shaping, if you're replicating this environment, feel free to do so. So let's start our capture. Now, my GNS3 has changed a little bit from our previous video because what I did was I was doing some other projects and doing some troubleshooting, and I upgraded to a beta version of GNS3. So if we go to Help and About, this is GNS3 8.4 Release Candidate 3. So it looks a little bit different, but the functionality is the same as our previous topology. So here's the access link to VLAN 10, this is the access link to VLAN 20, and this is our trunk link right here, and that's where we're going to capture. So let's go ahead and start our capture right here. I'm going to right click and say start capturing. Now before I do that, if you want Wireshark to automatically pop up as a running capture and so you can see the packets as they come in, one of the options inside of GNS3 is under Edit and Preferences under Capture. If you want to see the actual, the packets come in, you can actually click this. It'll open up Wireshark so you can see it real time or very, very close to real time. If you just want to save that capture file and then look at it later, you don't need to click this. But what I'm going to do is I'm going to go ahead and I'm going to leave that checked for now so we can actually see the packet capture. Click OK. And actually, before we start capturing, let me go ahead and add the labels back so we can see exactly what they are. So on the switch, it's FA11 and R1 is gig1/0. So let's have some fun and generate some traffic. We'll right click on Start Capturing, and go ahead and start the capture process. Now, this new window that pops up is Wireshark. Any traffic that is seen on this link right here should be shown up in this window. All right, so here we have some browser activity, a CDP message, fantastic. So we know it's working. I'm going to put that in a separate window just for a moment, and let's generate some traffic. Let's go to our Windows 8 machine just to verify that he really is on the 10 subnet, do an IP config, and he says, yep, sure enough, I'm on the 10 subnet, which should be traffic shaped. Any traffic coming back to them should be limited to 64 kilobits per second. So let's go ahead and open up a browser, and his default homepage is Google. If you notice, it's taken a few seconds for just the basic page of Google to come up. So now let's go to a machine that's not on this subnet, but it's on subnet 20 that's not having any traffic shaping applied to it. Our good volunteer is right here, this Ubuntu box. So we'll bring up a command line and do an if config just to verify that this machine really is sitting on the 20 subnet, which it is, fantastic. And let's open up a browser. And notice that came up much, much more quickly. So if we did a really quick search for example, images, and we said CBT nuggets, like that. See how the images come up very, very quickly right here? If we went back to the Windows 8 machine and we did that same exact thing. So now we're back at Windows 8. We'll click on images. It's taking time for even this page to reload. And we'll type in CBT nuggets and click on search. You'll notice how there's just a painful delay as far as this screen populating with anything. At 64 kilobits per second, it's going to take quite a while to get our graphics coming up. So I'm not going to put you through all of that pain, but I do want you to see how slow it is. Now, if this was happening for your users and you're wondering, oh my gosh, what's going on? Is it just one website? Is it our network? Where is the problem? Is it the client itself? Where's the problem? We could take a look at the capture file that we just collected and start to take a look at where those delays are showing up. So let's stop our capture. Back in GNS3, we'll right click and say stop capturing. And now we can look at the details of that capture file. So here's what we're going to do. This file right here, which was just captured, I'm going to go ahead and save this. I'm going to call it Latency. And I'll make it available in the Nugget Lab download area. So you can download it, look at it, open it up, and follow right along with me if you'd like. If we want to see how bad it really was from the router's perspective, it can tell us. We can just do a show traffic shape statistics, and it will say, okay, here's what happened. So regarding the delays, here's the packets and bytes in general, and as far as delayed packets and bytes, so most of the packets coming back to our Windows 8 machine up on VLAN 10, most of them were being delayed by this router. And the reason we did it was to simulate some latency, some excessive latency in the network. So you and I know, we both know exactly what caused the delay here. It was the traffic shaping that we injected on our own router. However, if this is a production environment where we weren't sure where the delay is, we could ask ourselves, is it the client? Maybe they're getting the responses back from the server, but just not, repainting the picture because they're so overwhelmed or whatever else is going on. Is it something in the path between the client and the server? Or is it the server causing the grief on the back end? one of the things that Capture can help us identify is that if we make requests, for example, and we get responses that come back in, 25 or 26 milliseconds, we can pretty much rule out the path and the server. I mean, if we give a request, we get a response back, and the client isn't making the next request or isn't processing that data, we could then look at the details of that client, what's going on that computer. Now, in our nugget on profiles, we created a new column, and that new column was based on the delta for TCP segments in the same stream. For taking a look at this capture file, that column is going to be extremely helpful to us once again. In that profiles nugget, if you created that new custom profile, you've already got that column. But what I want to do in this video is share with you yet another way to bring your profiles with you. So if we want to get that TCP delta as a column again, we could manually add that back in. Currently, I'm using my default profile, or we could go to the custom profile we made in the profiles video, or we could create a brand new profile that adds that column as well. Here's what I'd like you to do. In the Nugget Lab area, I have put a preferences file for you. It's right here. And this preferences file is very, very similar to what we did in custom profiles, but I also wanted to walk you through how you could back up and also implement your custom settings wherever you go. So let's say, for example, we want to take this preferences file and we have it on a network share that we have stored, or we have it on a thumb drive that we carry around with us. What I'd like you to do for this video is I'd like you to practice in adding a brand new custom profile and use this preferences file, which I'm going to use in this video. So how do we add it exactly? So I'm going to open up this preferences file so we can see it. I'm going to say, please open it up with Notepad. So it's just a configuration file. I backed it up from one of my favorite profiles that I had. So it's just a text document. Let's go ahead and close it. I'm going to right click on this and copy. So now I've got it copied to my clipboard, to my buffer. Next, we're going to go to Help, About Wireshark, which is exactly what we've done in our nugget on profiles. Click on Folders, and I'm going to double click here on Personal Configuration. On a Windows machine, that's going to take me to my Wireshark folder, not where I installed it, but where it's going to keep my custom files. And right here under Profiles, all I need to do, if I want to create a brand new profile, and I'd like you to do this as well right now with me, is double click on Profiles. There's the custom profile 1 from our Profiles nugget. I'd like to create a brand new profile by right clicking, selecting New folder, and let's call this Latency Profile, meaning a profile we might use if we're looking for latency. Then I want you to go into that folder and check this out. So we're sitting inside the latency profile folder, and all I'm going to do is right click, and I'm going to paste that preferences file right there. So what we've just done is we've created a brand new profile, and now we can go ahead and start using it inside of Wireshark. Check this out. I'm going to go ahead and minimize this. I'm going to close this window. And then back at Wireshark, if we go to Edit, Configuration Profiles, and now we have the default, which I'm currently using right here. I've got Custom Profile 1, which we created together in the Profiles video, and I also have this new Latency Profile that I can go ahead and start using if I want to. We could either use the status bar down here to change it, or since I'm right here, I can click on Latency Profile, click on OK, and I'm now using the Latency Profile, which includes in that profile the TCP delta. Now, if you want to set that up from scratch, the TCP delta, you certainly can. The details for doing exactly that are in the profiles video. If you want to revisit that, please feel free. So now if we're looking for latency issues, what we could do is this. We could go ahead and sort by time since previous TCP, right click, and say sort descending, and then use this icon here to go to the very first packet. And as we take a look at this, 81 seconds. Now, that seems really bad, and it very well could be, but these are closing sessions. There might have been a session that was established quite a long time ago, just some background activity in closing an existing session. So I don't think any of these are really causing the user grief as far as delay. I do notice this one here at 12 seconds is an eternity for anything. So, and this was 20.2. This is our Linux box, 12-second delay it was doing a get for an image here, a PNG file. And that very well could have been something not too critical. For example, the web page came up, and then in the background, it actually brought in some more content. That could have been a background little image. So some of these we can rule out as being a huge problem. But if we scroll down, again, all the ones that are closing TCP sessions are probably not too critical for our customers. But that would be an approach to start identifying exactly where there's some delays within a TCP session. So these are the worst of the worst. If we go to the other side, the flip side of the same conversation, way down here near the bottom, for example, because we're sorting in descending order, look at all this traffic with a 1 millisecond delay. At least that's what it's reporting. So we open up the details of that, and we go down to timestamps just to confirm, saying time since previous frame in this TCP stream, it's reporting 0.001 seconds, which is 1 millisecond, which I think sounds a little too good to be true. But then again, the packets aren't lying. This is just what Wireshark saw as the traffic came in. One other thing I'm going to do right here, because we're in this latency profile, I'm also going to remove the bytes pane down below. So we'll go to View, specify packet bytes, because I don't want to see that as well. And that change as well becomes part of my latency profile. In this nugget, we've identified that there's quite a few variables involved when the user says, hey, the network seems slow. Could be the client, could be the path between the client and the server, or it could be something on the server and the back end over there. A really cool feature to use is that delta for a TCP stream to find out if there's huge delays between a request and a reply. So if the client makes a request and 10 milliseconds later we get the response, and the client's claiming or feels like it's really, really slow, maybe there's something going on inside that computer that's causing that slowness or that effect of slowness. If the client makes a request and 2 or 3 full seconds later the replies come back in that case we could blame the delay on something in the path or on the back end at the server. We also identified how we can take our profiles with us by simply creating a new folder and copying the preferences file that we brought with us into that folder as the profile we can go ahead and use. If you haven't done so already, I would strongly encourage you to get a baseline of your current network, or at least of your current PC as you do various activities. The information that you gather and look at as a baseline will be helpful not only in understanding the basic traffic that's on your network, but also to identify problems that might have been there all along that you want to go ahead and investigate and to clear up. I hope this has been informative for you, and I'd like to thank you for viewing.